The pushes and pulls of forces literally make the world go round, and they are fundamentally important in life and in the study of life, including physics. Now, we've already looked at forces to some extent. We're going to now need to think about what the forces are acting upon, and for that there's going to be an area. So we're going to be looking at pressure, and we will look at the equation that everyone knows. But I'm going to want to spend more time in this lesson video also looking at hydraulics, so we can understand how they work, which is incredibly important in our modern robotic world. The equation for pressure, the defining equation that is P equals F over A. Pressure equals force over area. Force is in newtons, area is in meters squared or centimeters squared. So pressure is in newtons per meter squared or newtons per centimeter squared. It's such an important quantity though that it gets its own special unit, the Pascal, after Blaise Pascal, a French mathematician and physicist who started changing the world as a teenager. Anyway, 1 Pascal equals 1 Newton per meter squared. The significance of the equation appears when I try to put a pin in a board to hold up a poster. Obviously, I'm going to push on the big side, and the small point will be against the wall. Push, and the pin slides in, breaking the surface. If I turned the pin around, there would be a lot of screaming and pain as the pin would slide into my thumb, breaking the skin. The small area, with a constant force, means the pressure is high, and high pressure can break things. So, let's put this knowledge to use by looking at hydraulics. Hydraulic machinery uses liquid to transfer forces. It's used to make robots move, suspension in cars, and mechanical diggers, which is probably the most likely example to come up in a test. They work by using the fact that liquid cannot be compressed. So, if you put one area of a liquid under high pressure, that pressure will pass through into all parts of the liquid. It works best with oils, which have these massive long molecules that prevent squashing, but at GCSE we'll assume it works just fine with water too. So we've got this tube here, and I'm going to push on this end. I'll push with a force of 5 newtons on this end here, and the tube has a cross section of 10 centimeters squared. So there's a pressure I'm creating inside the liquid, and we can work that out. P equals F over A equals 5 over 10, 0.5 newtons per centimeter squared. Note this is not pascals because 1 pascal is 1 newton per meter squared. There's no need to try and convert. The answer is correct already. Right, so down the other end, the pressure is transferred perfectly by the liquid, and the area is still the same. So we have a pressure of 0.5 newton centimeter squared and an area of 10 centimeters squared. So P equals F over A becomes F equals PA equals 0.5 times 10 equals 5 newtons. The liquid at this end will push with a force of 5 newtons. So how far will it move this block here? Well, if I pushed in 4 centimeters and the area is 10 centimeters squared, remember, that means I moved a volume of 4 times 10, that's 40 centimeters cubed of liquid was pushed in by me. At the other end, I need to move the same volume of liquid, 40 centimeters cubed, with the same area, 10 centimeters squared. So the length is V equals AL, L equals V over A equals 40 over 10. The length is 4 centimeters, the same as at the other end. That's the simple example. In hydraulics, they often change the cross-sectional area of the tube, which turns this simple machine into a force multiplier. Let's look at an example. Here I have a tube, but the area is 10 centimeters squared on the left and 20 centimeters squared on the right. We'll push with a force of 5 newtons again and see what happens. First, the pressure on the left is P equals F over A equals 5 over 10 equals 0.5 newtons per centimeter squared. Okay? This pressure is transferred through the liquid perfectly, so the pressure on the right is also 0.5 newtons per centimeter squared. Now the force on the right is going to change. Using P equals F over A, so F equals PA, now we have F equals 0.5 times 20 equals 10 newtons. The right hand side is going to push with twice the force of the left. Now this is going to be handy. Imagine if you wanted to lift a car, or let's say you wanted to lift something a bit more easy, a 200 kilogram box. You'd need a force of 2,000 newtons to do that. But with this machine, you could push on one side with only 1,000 newtons and the other side would have enough force to lift the box. It sounds too good to be true, so let's see what we lose. If I push in 4 centimeters like before, the volume I displace is still V equals AL equals 10 times 4, 40 centimeters cubed. On the right, I need to displace the same volume of liquid. So L equals V over A equals 40 over 20 equals 2 centimeters. I only moved 2 centimeters at the other end, half of what it was on the left. So my force multiplier doubled the force but halved the distance moved. That means I still end up doing as much work, but it is easier work. Now there is an easier formula you can use to calculate this. Because the energy used, the work done is just force times distance, W equals Fd. The energy on the left is equal to the energy on the right. So 5 times 4 equals 10 times 2. More generally, I'll sketch this out again. F1 over A1 equals F2 over A2, since the pressure is constant. And for the distance moved, F1 times D1 equals F2 times D2, since the work done is constant. We'll look at work done more later in the course. Now obviously, pressure has got loads of applications in physics, engineering, and just life in general, so it's going to come up again and again. We've looked at the basic idea, P equals F over A, so we can work out things, but we've also spent time looking at hydraulic systems, so do take time to understand how these machines actually work, so you can put your ideas and your understanding of pressure to good use in the real world.